Alright class, welcome to the video on Learning Outcome 18 for Math 2015. In this video, we're going to extend the base 10 multiplication methods to correctly model polynomial multiplication using manipulatives, pictorial representations, verbal descriptions, and variable expressions. Okay, so we're multiplying polynomials today. How do we define multiplication? Do you recall what we talked about in Math 2010? Multiplication is efficiently counting objects. We are looking for a total when we have equal groups. So we arrange our objects into groups of the same size, meaning that A times B is the total in A groups with B objects in each group. So I call it groups of objects. You can think about multiplication as one quantity when it's a multiple of another, objects in an array, and the area of a rectangle. So we're going to use the area of rectangle mostly today. Multiplying polynomials. Let's model something with whole numbers, then we can to recall how that works, and then we'll connect it to polynomials. Okay, we're going to model 21 times 13 with base 10 blocks. And with base 10 blocks, when you model something, you use a key. Okay, so here's our key. We're doing whole numbers, so we're going to use the traditional key of the big block corresponding with 1,000. We have the flat corresponding with 100. We have the rod corresponding with 10. We have the little cube, which I indicate with a dot, corresponds with 1. And so when we're going to model with base 10 blocks, we arrange these blocks in a rectangle. Okay? When we're going to use the rectangle approach to multiplication. A rectangle will have a horizontal and a vertical dimension. So I'm going to model 21 first with the horizontal dimension. Okay, so 21, which we're going to lay two rods together here in a row, and then that one. And then we're going to do a couple of bars here to kind of separate out the area model from the problem and the answer. The 13 will have a rod this way and 3 ones going down this way, the vertical dimension. We're going to fill in the product by bringing the horizontal dimension down and the vertical dimension to the right. Okay, and looking at the intersection. So for the first column here, we have 1 times 1, or 10 times 10, which is 100. And we'll have 10 times 1, which is 10. Filling in here, 10 times 1 again, and 10 times 1 again. As we move over to the next column, we have another 10 there, so we'll do 10 times 10 here. Then we'll fill in the same way with these rods. And then we'll do 1 times 10 for the last column. 1 times 1 will give you just 1, and come down in this way. Okay, so the product is actually inside my graphic organizer here, so the grids. We have 100 here and 100 here, so that's 200. 10 here, so that's another 60, 260, 270, 271, 272, 273. Okay. So in summary, 21 times 13 is equal to 273. Okay, so base 10 blocks. Now we're going to model 21 times 13 with the open box method. It's an area model. Well, we're going to draw a box, or rectangle, that will model 21 times 13 with 21 on one dimension, 13 on the other. So we'll put the 21 on the horizontal dimension and 13 on the vertical dimension. With the open box method, we're going to break up our numbers into easier numbers to work with for multiplication. 21 can be broken up into 20 plus 1 if we follow our place value. 13 can be broken up into 10 plus 3. Now we're going to find the area of these smaller rectangles using the easier dimensions. 20 times 10 is this one, which is 200. This one is going to be 20 times 3, which is equal to 60. And this one we have 1 times 10 is equal to 10. And then the last one we have 1 times 3, which is equal to 3. Our partial products include 200, 10, 60, and 3. We're going to add all of those up to get our answer. We get 273. So that's the open box method. We're going to model this with partial products. Okay, recall that partial products is almost like the algorithm. So we'll set up our numbers vertically, and we write down every product that we use to calculate the answer. We separate the number into 20 plus 1 times 10 plus 3. Okay, now we can see all the partial products are. So we do 3 times 1 is 3. 3 times 20 is 60. 10 times 1 is 10. And then 10 times 20 is 200. And then we also have our 273. Okay. So 273 for that answer. Those are the partial products. Notice that the partial products are in the rectangle. Those are the same as the ones in the partial products algorithm. Modeling with algebra tiles. We want to model 2x plus 1 times x plus 3. Or, in other words, more precise words, we want to model the quantity 2x plus 1 times the quantity x plus 3, because they both are in quantities, they're both the same, they're both like one quantity, one number. So that's why they group them with parentheses. But we can operate on them separately. We want to model this with algebra tiles. Okay, and so we'll go ahead and do that. Okay, here is the example solution for 2x plus 1 times x plus 3. We can also say the quantity 2x plus 1 times the quantity x plus 3, because we're trying to multiply both of them together. So we want to set up the actual problem with algebra tiles. And here at the bottom of the screen I have all of my algebra tiles set out. We need to do 2x plus 1, which means I'm going to take 2x bars here and set up at the top, line them up there, and a positive 1 square and line it up there. Then along that's the horizontal dimension, and then along the vertical dimension for this area model, we're going to set up x plus 3. So there's x, take 3, of the positive 1 squares, okay, for algebra tiles. Okay, now that I've set those up, we're going to fill in the area model by bringing all of these down and all of these to the right, okay, and see how they intersect one piece by one piece. Okay, so we're going to start with the x and the x intersection, which gives you x squared. So place our x squared in that spot. Keep going down here on this first x stick column. We have x and 1. And x and 1 make x, so we're going to go put our x bar right there. The next thing that we're going to do is we're going to put another x and 1 and another x and 1 here. So we're going to fill in 2 more x and 1s. So x by 1 and x by 1. Okay. As we fill towards the right, we're going to look at the second column of x here, which has an x intersected with another x, which means we have another x squared piece there. Then we have 3 more x's here because of this x column and then these 3 ones. Okay, so we're going to fill in these x's. The x sticks here. Okay. And as we do that, we have one more column left to do to fill in, which will be 1 and then the x, which makes x here. And then 1 and 1 match up here. And another 1 and 1 match up here. And another 1 and 1 match up here. Okay, so once we've filled in everything, we're just focusing on this part that's all filled in with algebra tiles. Okay, so the product of 2x plus 1 times x plus 3 is this part right here, where we'll count it. 1, 2, 2x squared. And so we're going to record as we count. So there's 2x squareds there. And how many x bars do we have? X sticks. 1, 2, 3, 4, 5, 6, 7. We have 7 x ones, x sticks. And I have 3 units. Okay. So the product of the quantity 2x plus 1 times the quantity of x plus 3 is 2x squared plus 7x plus 3. Next we're going to model 2x plus 1 times x plus 3 with the open box method. So the open box method is going to be similar as what we did for our whole numbers. There's 4 rectangles. This one is 2x plus 1. This one's x plus 3. Now this would be representing x, this distance here. This is 3. This distance right here is 2x and 1. Okay. Now we're going to go ahead and multiply each part. So 2x times 2x is 2x squared. 2x times 3 is equal to 6x. 1 times x equals x. And 1 times 3 equals 3. Just like we added them all up here, we're going to add them all to 2x squared plus x plus 6x plus 3. When we add all of these together, we're going to get 2x squared plus 7x plus 3. Okay, so we have all of that done with our open box method. Seeing the partial products here. And speaking of partial products, let's go ahead and do that. To see these partial products, I'm going to write it horizontally. And use a form of the distributive property, where we multiply each part. Okay, so we're going to multiply 2x times x plus 3 plus 1 times x plus 3. And then I can go ahead and distribute again. Do 2x squared plus 6x plus x plus 3. And that gives me 2x squared plus 6x plus 3. Let's insert this. I just thought of 2x times x. Here's our first one. Plus 2x times 3. Second one. plus 1 times x plus 1 times 3. Okay, so when you get all of those together, you get 2x squared plus 6x plus 3. Those are the partial products. We're going to model this with algebra tiles. X minus 2 times x minus 4. In this problem, we're modeling the quantity x minus 2 times the quantity x minus 4. Again, we will have a horizontal dimension and a vertical dimension for our area model. And we want to set up x minus 2. So we'll take an x first here. We'll take an x bar, put it right here, and 2 negative squares here, 2 negative units. So there's our x minus 2. Subtracting 2 and negative 2 are very similar. And for our vertical dimension, we're going to do x minus 4. So we'll put our positive x bar here, and then rod, and then minus 4. Minus 4 units down that way. Okay. So when we're going to fill in our area model, we're going to fill in down and to the right. So x and x intersect right here. So we'll have our x squared algebra tile there. When x and a negative 1 intersect, they make a negative x. So we're going to take a negative bar here and put it right there. And then I'm going to take the negative bars and put it here, here, and here to fill in the rest of that column. Okay, so now we have our x times the x minus 4 column. Now the next column here is the negative 1 times everything. And the negative 1 and the x together make negative x. The negative 1 and the negative 1 here make a positive 1 here. Okay, so be careful of that. It makes it positive. And we fill in our positives here because we're having negative 1 times those other negatives. So filling that down, they're all positives there. Okay. And our last column is a negative 1 as well, so we're going to see where it intersects with our negative x. So put our x bar here, negative x. And again, like in the previous column, we'll have negative and negative 1, the intersection of negative 1 and negative 1, so we'll fill in those with positive ones. Because we remember that a negative times a negative is a positive. Negative times a negative is a positive. Okay? So fill those in there. So once everything's filled in down and to the right, we can now take a look at all of the pieces and add them together and put them in symbols. So when there's 1x squared here, the next is the category of pieces is x's. So we have 1, 2, 3, 4, 5, 6. 6 negative x's. So put minus 6x there. And then we have our positive ones. 1, 2, 3, 4, 5, 6, 7, 8. So we add 8 here. So the quantity x minus 2 times the quantity x minus 4 is x squared minus 6 plus 8. As we can see here symbolically, abstractly with the numbers, and then concretely with the algebra tiles. Here we're going to model the quantity x minus 2 times the quantity x minus 4 with the open box method. Okay, so let's go ahead and do open box. Okay, so the subtractions will become negatives with the number before and number after it. Okay, so all the numbers have their sign before. When we do x times x, we get x squared. We do negative 2 times x equals negative 2x. And then we have x times negative 4, which is equal to negative 4x. And we have negative 2 times negative 4 equals 8. Because the negative times negative is positive. Negative times negative is positive. Okay. Our answer then is x squared minus 2x minus 4x plus 8, which is equal to x squared minus 6x plus 8. We want to model this with partial products, so I'm going to write them out again horizontally. Take all of this multiplied by x and all that multiplied by minus 4. Then I'm going to go back and distribute into here and get our partial products. Okay, so that negative 4 here becomes negative 4x there and minus 8 plus 8. Okay. So I think we have it now. We have x squared minus 6x plus 8. That's our answer. Let's take a look at another one in model with algebra tiles. X plus 3 and x minus 2. The quantity x plus 3 times the quantity x minus 2. All right, for this example, we're finding the product of the quantity x plus 3 times the quantity x minus 2. Okay, so we're using area models. We'll have a horizontal dimension and a vertical dimension to multiply together. In the horizontal dimension at the top, we're going to model x plus 3, our first factor. So we have one x, positive x unit, rod. We have 3 positives for the x plus 3. All right. Now we're going to model the vertical dimension with x minus 2. So our positive x here, and put in a negative 2 here. So 2 negative units. And then when we find the product, we're going to fill in down and to the right. Starting with this column of x, we know that x times x makes x squared. So put our x squared there. X times negative 1 is going to be the negative x. So put a negative x bar here. And then the x times the other negative 1 will have another negative x bar here. Going from this column here, we have the positive 1 times x, which is going to be a positive x. Positive 1 times the negative unit gives me another negative unit. Okay. Negative 1 times positive 1 is negative 1. Then I have the positive 1 times negative 1, gives me another negative unit here. Next, we are going to do this column here, which is a positive 1. It will mirror what we did in the previous column. So positive 1 times x, positive 1 times negative 1, negative 1, positive 1 times negative 1, negative 1. So filling in. Okay, same thing with this third column. Take a negative 1 here, negative x, or negative 1 unit. This is a positive x, negative 1 unit, negative 1 unit. Okay, so we filled in everything down and to the right. And we're going to sum what we have in our algebra tiles and put it in abstract terms with the symbols and the numbers. Recall that when you have, let's go ahead and do the x squared one first, because there's only one of those. Okay, so that was taken care of. Recall that when you have a negative x here and a positive x here, those will become a 0 pair, and they will go away. Okay, so we're going to take those away. Okay, we have another negative and positive x here, so we'll take those away to become a 0 pair. The x's that we're left with is 1 positive x, so we're going to put plus x here. And then of the units, we have 6 negatives here. Okay, so negative 6. Thus, the product of the quantity x plus 3 times the quantity x plus 2, x minus 2, is x squared plus x minus 6. Here we're going to model x, the quantity x plus 3, times the quantity x minus 2 with the open box method. So we're going to model x plus 3 on the top here, x minus 2. At each part, we have x times x equals x squared. Three times x equals 3x. Negative 2 is negative 2x. And we have 3 times negative 2, negative 6. So in all, we have x squared plus 3x minus 2x minus 6 equals x squared plus x minus 6. Okay. The partial products method, we're going to go ahead and use the distributive property. We take this whole thing times it by x, this whole thing times it by negative 2. Then we're going to go this way. And get our x squared plus 3x. Then we get our negative 2 is x. Negative 2, negative 3. So we have x squared plus 3x minus 2x. So those are x squared plus x. And then negative 2 positive here. Minus 6. So how do we model this? What would this look like? Here's our open box method to model it. X and minus 4, x and y, and 3. So we would do x times x equals x squared, y times x equals xy, 3 times x equals 3x. And then we have x times minus 4 equals minus 4x. Y times minus 4 equals minus 4y. We have 3 times minus 4 is minus 12. When we get our partial products, we have x squared plus xy plus 3x minus 4x minus 4y minus 12. And simplifying by adding like terms together, x squared plus xy minus 3x minus 4x makes minus x. for y minus 12. The problem with FOIL. Now when we're doing x times x, quantity x plus 3 with the distributive property, we get multiply this way. X squared plus 3x. Now when we're doing FOIL, we do 2x plus 3 times x plus 1 with FOIL. So we do the first, the outers, the inners, and the lasts. FOIL is a acronym for the order which you do this. So you have first, which is going to be my 2x plus 2x times x. Outers, which is going to be my 2x times 1. Inners, which is going to be my 3 times x. And lasts, which is going to be my 3 times 1. So those are my partial products. 2x plus 2x squared plus 2x plus 3x. Plus 3, 2x squared plus 5x plus 3. Okay, so there's that one. So how do we do the first, how to change the last? So how do you do that with this one? Okay, and that's where the distributive property comes in handy. The problem with FOIL is that just for binomials times binomials. Okay. But it has no meanings. It has no meaning when you have a trinomial or any other polynomial. Okay. So when we do have something like this, we have to use the distributive property like we've been doing before. X plus y plus 3 times x minus 4. We'll distribute that to the x and then to the 4. X plus y plus 3 times x minus or plus x plus y plus 3 times negative 4. Okay. And then we have to go back to here. Go back to here. X squared plus xy plus 3x plus minus 4 times x plus minus 4 times y plus minus 4 times 3. That will give you the x squared plus xy plus 3x minus 4x is minus x, and minus 4y minus 12. Okay, that's what you have to do. And that's what's the problem with FOIL, is that it's only good for binomials, tens of binomials, and so we can't generalize it to other polynomial multiplication easily. And that's what we have for our video. Please let me know if you have any